So we get into the final part of energy conservation, and we end it on energy conservation in higher dimensions. Watch the previous episodes for energy conservation in 1D. Welcome to my advanced physics class, where we discuss modern physics and classical physics. Kindly subscribe, click on the notification bell, comment, share, and like my videos. So for energy conservation in higher dimensions, we begin with the XY plane, that is in 2 dimensions. For the XY plane, let's just say an object is located at this point, and then a force moves this object on a crooked trajectory to point 2. So at any point on a trajectory, the force that moved it could point in any arbitrary direction. So that means this force becomes a vector. And the position vector, a very minute position vector, we call it the R. So we ask ourselves, what is the analogy of the law of energy conservation in 2D as we did in 1D? So we get back to first principles. That says that the work done by a force is equal to the change in the kinetic energy. So let's go to the explicit formula for the kinetic energy. Now, kinetic energy is equal to half the mass of the object times the velocity squared. So then in 2 dimensions, v, which is velocity, also becomes a vector, unlike in 1 dimension where it is not a vector, because negative and positive killed every kind of misunderstanding about whether it is to the left or to the right. So this time round, it is a vector. So then we write the kinetic energy formula as half m v, which is the magnitude of the velocity, squared, is going to be vx squared plus vy squared. Now this is gotten from Pythagoras theorem. So v squared is equal to vx squared plus vy squared. And that is the magnitude of the velocity squared. So the magnitude of the velocity itself is the square root of that, vx squared plus vy squared. But here we want v squared, that's why we remove the square root. Then let's find the change in the kinetic energy. With respect to time, we have decay dt to be equal to half m into bracket. Then we differentiate vs squared. We need to be careful. You have to differentiate the outside, then differentiate the inside with respect to time. So for the outside, we have 2 times vx, and for the inside, we have the change in vx with respect to time, the vx dt, plus 2 times vy, the vy dt. That is a change in the kinetic energy with respect to time. So the kinetic energy, the change in the kinetic energy with respect to time, let me write that again, is equal to half m into bracket. Now we have 2vx dvx dt. Now the vx dt, if you could recall, is a change in velocity with respect to time, and that is acceleration. So we have 2vx, and we write ax for dvx dt, plus 2vy ay. Now pushing the half throughout, and then every other parameter into the bracket, we have m vx times ax plus m vy times ay. That is a change in the kinetic energy with respect to time, decay dt. Now rearranging, we have m ax vx plus m ay vy. That is decay dt. Now we could record that max from Newton's second law is a force. So this is equal to fx, the force in the x direction, vx, plus fy, the force in the y direction, times vy. That's equal to decay dt. This is the first quantity we have stumbled upon. Now, decay dt, which is a change in the kinetic energy with respect to time, is called power. In physics, we call this power, the change in energy with respect to time, the rate at which work is done, is equal to the F component of a force vector times the S component of a velocity vector plus the Y component of a force vector times the Y component of a velocity vector. And we call this a dot product. So if you ask how physicists stumbled upon dot product, it came from work done. So then the mathematicians will take over and then delve into it more and see how it goes. So we can write this power, decay dt, as a dot product, a force vector dot a velocity vector. That is what physicists do. They stumble upon an idea, then they give it a name. We call this a dot product. Now, this is the change in the kinetic energy with respect to time, but we just want the change in the kinetic energy alone. So let's multiply through by dt. By so doing, we have decay, which is a change in the kinetic energy, is going to be equal to fx vx dt plus fy vy dt. Now this quantity vx dt is a dx. Velocity multiplied by a change in time is a displacement. So decay is equal to fx dx plus fy dy. So we now see that a little change in kinetic energy is also a dot product. So this can be expressed as a force vector dot a tiny position vector, that is decay. And this decay is a minute change in kinetic energy expressed as the dot product of a force vector and a tiny position vector. So let's just say we make a long trip. See, and this one is such that in the xy plane you have a force vector that does this, and on a minute part of the trajectory you have little dr, and you have the force vector at this point pointed in any arbitrary direction. So f dot dr from this point to this point, which is an infinitesimal displacement, is what gives you this infinitesimal change in kinetic energy. So if you make a long trip from this point to this point, then you integrate decay from point 1, which I will call 1, to 2, is equal to the integral of that force dotted with dr from point 1 to 2. Now point 1 to 2 means from a location r1, this is a vector now, then to a location r2, which is also a vector. No? So this integral of little decay from point 1 to 2 will give you delta k, that is k2 minus k1. So is equal to the integral of f vector dot dr vector from r1 to r2. So in higher dimension, the analogy of the law of conservation of energy is such that right now the integral of the force vector, no more in one dimension, it is a vector dot dr from r1 to r2 is equal to a change in kinetic energy. So if you can do this integral, then you express it as a change in kinetic energy. So the problem now is to look out if we can do this integral. Can we express this integral as a potential at 1 minus a potential at 2? What I'm trying to say is that this integral of the force vector dotted with dr from r1 to r2, is it equal to, say, u at r1 minus u at r2? That is a great question mark. If we can do this, then we are cool to go. We have also solved the problem in multiple dimensions. But in general, this doesn't work. It doesn't work for all forces. Stay tuned. In the next episode, we are looking at if we can express this integral as a change in potential functions. Kindly subscribe, click on the notification bell, and like my videos.